All right, so we talked about uh, what happens when we have s orbitals and we're making molecular orbitals. Um, we started off trying to explain this oxygen weirdness about how it's paramagnetic and attracted to the molecular magnetic field. We didn't actually get to explaining that yet because we're kind of working our way up to it. But we left off thinking about our second period diatomics, and we want to think about now. Um, Once we get past beryllium, we're going to need to think about including p orbitals. Okay, and so there's two things we want to remember here. The number of atomic orbitals we put in should be equal to the number of molecular orbitals we get out. Okay, so if we overlap two things, we should get two things back out. And what we saw last time was if we took an s orbital and an s orbital and overlapped them, we got an antibonding and a bonding orbital. And that's going to be true with these as well. Okay. Um, Now, when we're talking about p orbitals, we're talking about there's two ways they can overlap. They can point at each other, or they can be parallel to each other. So let's take a look and see what this looks like and how that has an effect, what the outcome is with the molecular orbitals. Okay, so if we take two p orbitals and point them at each other, okay, we're going to get a 2p, a sigma 2p, and a sigma 2p star. We're always going to get a bonding and an anti-bonding orbital. Okay, remember these are sigma bonds, right? Because we're pointing at each other. They're pointing at each other and on overlap along the bond axis. So they are literally connecting the atoms together here between. Okay, they look a little different than the sigma 1s or 2s because they have this little blip on the outside here, okay, or this little blip on the inside here, which is not present in the 1s's and 2s's. Okay, don't worry about it. Okay, just look for that end on overlap along the bond axis. Okay, remember here's our node in the anti-bonding orbital that is breaking the bond. So the bonding is making a bond and the anti-bonding is breaking a bond. But again, only if we put electrons into that anti-bonding orbital. Okay, so again, this is the anti-bonding and the bonding looking at the same time. It's got that kind of wrapped candy look to it. Um, all right, so what happens if our orbitals are parallel? Do we remember about parallel p orbitals? I hope so, because the same thing is true in valence bond theory that's it's true in molecular orbital theory. Okay, I don't know why I'm making this pop up so slow. Okay, if we have parallel p orbitals, and they'll overlap sideways, we're going to get pi bonds, and we're going to get a pi bonding and a pi anti-bonding molecular orbital. Okay, they are both right. Here's our nuclei, so we can imagine. Can't control PowerPoint, but I can imagine that this is the plane of the molecule, right? Those dots there are our atoms involved, right? This is above and below at the same time. Just like we saw in valence bond theory, the pi bond is above and below at the same time. This is going to lock it in place and keep it from rotating. Okay. The anti-bonding has a node down the middle, just like we would expect. So I always picture the pi anti-bonding orbitals are like butterflies, right? They've got a thing out here, a thing out here, a thing out here, and a thing out here. If we're going to color them in differently, they're going to be looking like this. Okay. Uh, right. Now, there's two sets of p orbitals that are parallel. These ones are the easy ones to see because they're in the plane of the screen, right? They're in the plane of what's going on. The other ones are parallel to the floor. They're in the same idea as the floor or the table or whatever. They're perpendicular to the other ones, but it's the same idea. They're going to overlap sideways. They're going to give us a pi 2p bonding and a pi 2p star anti-bonding. The anti-bonding still has a node that separates it out. So we're making and breaking again. Okay. It looks the same. It's just rotated 90 degrees because it's perpendicular. Okay. This is another way to look at these p orbital overlappings, right? The antibonding is always going to have a node that breaks it. The bonding is going to be joined together. Sigma is along the bond axis between the two nuclei, and pi bonding is above and below. Okay. Now, the pi's always come in pairs. Okay, those pairs are degenerate. Do you remember what degenerate talk means when we talked about it before? Um, Remember, degenerate just means the same energy. So it's going to cause a little bit of a wrinkle when we go to do our orbital diagrams. Okay. So what we're seeing though here is if we're overlapping things that's going to involve the p orbitals, right? There are three p orbitals. Each atom has three p orbitals. So we take six orbitals, combine them together, we're going to get six molecular orbitals out. Okay. So it's going to complicate our molecular orbital picture a little bit, but we can deal with it. All right. Now, if you want to talk about it later, we can talk about it, but there are two different ways these molecular orbitals can line themselves up. Okay. There's this pattern on the right and there's this pattern on the left. And what's happening in here is it's based off of what atoms are involved. The only difference is in the middle. The sigma 2p and the pi 2p have swapped spots. Okay. The reasoning has to do with electron interactions and orbital touching each other's stuff and that kind of stuff. And we can talk about that outside if you want to. But just remember, if we're looking for is those big electronegative ones, oxygen, fluorine, or neon. If you have oxygen, fluorine, or neon, it's going to look like this. Okay. And if you don't, it's going to look like that. Okay. So let's take a stab at this. Remember, we always want to put an energy axis on these guys. I don't have it on this picture, but there we go. And for me, you don't need to be saying X or Y or Z. You can just say P star and S 2S star. Oh, I crossed out the S's. We need the S for the two S's. All right. So let's work something. Let's look at nitrogen. All right. We're going to make our orbital diagram. Since nitrogen, remember, I'll flat back over here. Nitrogen does not contain OF or NE, so we're going to be using this pattern. Okay. You need to get in the habit of knowing what these patterns look like. There's only two ways to do it. Okay. And it depends on oxygen, fluorine, or neon. Okay. Since we're doing nitrogen, we're going to use this left pattern. And the way I remember this, remember, draw your energy axis, right? 1, 2, 1, 2, 1, 1. Okay. We're going to label all of our bonds. Okay. So down here, one line means sigma. So go put all your sigmas in there. Two lines means we have pi. So that's a pi. That's a pi. Okay. The bottom ones are 2s. Everything else is 2p. Okay. Now you have three pairs of stuff. 2s, 2s. The top one is the 2s star. Pi 2p, pi 2p, this pi 2p is star. Sigma 2p, this sigma 2p is sigma 2p star. So we can find our bonding and anti-bonding things. All right, now, that's the diagram. We got to put our electrons in there. Nitrogen is in group 5. We have 2 nitrogens. That's 10 electrons. So put your 10 electrons in there. 1, 2. Remember, we're being off bow. 2. Okay. Now we go up here. 1. Remember, Hund's rule says 2 over here. 1, 2, 3, 4. I lost count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So now we have a good picture. Based off our picture, we're going to ask follow-up questions. And I always ask the same kinds of follow-up questions when we do this. Okay. Determine the bond order. Remember, bond order is 1/2 bonding minus anti-bonding. Well, there's bonding, there's bonding, there's bonding. That's 1, 2, 3, 4, 5, 6, 7, 8 bonding electrons. Anti-bonding is these guys. So that's 2. 8 minus 2 is 6, and half of 6 is 3. This is a bond order of 3, which makes sense because we expect a triple bond in our Lewis structure. Okay, net bonds. Remember, now this is going to cause us to remember that anti-bonding electrons cancel out the bonding electrons. Okay, so when we're looking at this, okay, this is a sigma 2s and this is a sigma 2s star. They're both full. Those cancel out. In the pi 2p, there's nothing there. So those are still there. And there's nothing there. So those don't cancel out. So if we look at it for nets, net sigma, let me do it this way. There are 1 net sigma and 2 net pi's. right? There's one, and there's one. Okay. The trick here is if you take 1, 1 plus 2 equals 3, 1 sigma 2 pi is a bond order of 3. These things should add up to work for us in our favor. Okay. Next up, we want to know, is this paramagnetic or diamagnetic? Look for unpaired electrons. Do we have unpaired electrons? No. So this must be diamagnetic because there's no unpaired electrons. Okay. And lastly, we're going to compare N2 versus N2 minus versus N2 2 minus. Okay. This might get a little weird. Let's think through it. N2 is what we just did. Think about bond order. Okay. This has a bond order of 3. Okay. If we have N2 minus, purple. Okay. If we have N2 minus, that means we've added one more electron. The next electron goes there. Okay. We added an anti-bonding, which means our bond order should go down, and we only added one electron, so it goes down by a half. So this is 2.5. Okay. N2 2 minus means we've added 2 electrons, so the next electron goes there. Okay. We added another anti-bonding electron, so that means this one goes down again by a half, so this is 2. Okay. Now the compare part could be whatever I ask you. Maybe it's which is longer, which is shorter, which is stronger, which is weakest, right? N2 with a bond order of 3 is the shortest and strongest. N2 2 minus with a bond order of 2 is the longest and the weakest. Okay. So you should be able to come up with that. Remembering that when you're doing this, you shouldn't get a bond order bigger than 3 or less than 0. Okay. All right, let's look at another one. O2. Yes, we have to do this one so we can figure out why oxygen is paramagnetic. You probably may already have a guess about this. All right, so there's our energy axis. We're going to draw our pattern. Oxygen has oxygen in it. Okay, so that has the other pattern. 1, 2, 2, 1, 1, 1. The naming trick I showed us over here will work the same way over here. All the single lines are sigma. The doubles are pi's. Okay. The bottom two are 2s. The rest of them are 2p. Okay. And the top one of each pair is a star. So it's 2s star, 2p, 2p star, 2p, 2p star. Okay. Now let's count our electrons. Oxygen's in group 6. There's 2 of them. So we have 12 electrons. Put our electrons in this picture. 1, 2, 3, 4, 5, 6, 7. Hund's rule says 8 over here. 9, 10, 11, and then 12 is over there. Okay, I'm not going to do this in order. Think it through. Paramagnetic or diamagnetic? Well, the data shows paramagnetic. The experiment shows paramagnetic. And it's paramagnetic because we have unpaired electrons. Okay, now let's do the other stuff. Bond order is 1/2 bonding minus anti-bonding. 1, 2, 3, 4, 5, 6, 7, 8 bonding. 1, 2, 3, 4 anti-bonding. 8 minus 4 is 4, divided by 2 is 2. So we expect a bond order of 2, which is what we see if we draw the Lewis structure. We expect 2. We don't see the unpairedness, but we see 2 bonds. Okay. Let's do our net bonds. Remembering what cancels out. 2s star cancels out the 2s, so that's gone. This 2p does not cancel out, so that's still there. Okay. This 2p and this 2p cancel one of them out, and this one cancels one of them out. So we have, and it's probably easier to think about it this way, and I erased my electron, damn it. There. Okay, those have canceled out and those ones stayed. So for net, we have 1 sigma. I never thought I'd draw a sigma backwards. 1 sigma and 1 pi, which equals 2, and 2 is our bond order, so that makes sense too. If we compare, this is O2, and O2 has a bond order of 2. I didn't leave myself enough room. Okay, so O2 has a bond order of 2. O2 plus means we've lost an electron. So the last one to go in is the first one to come out. So that's this one. Okay. We took an anti-bonding electron out. So our bond order goes up by a half. So O2 plus is 2.5. Okay. O2 minus means we've added one to O2. So I got to put this, now we have O2. We're going to add one more to O2, which means we have that. Now we've added an anti-bonding electron to the oxygen. So this means it goes down by a half. So O2 is 1.5. Oh, shit. I'm sorry. O2 minus is 1.5. There we go. Okay. So again, what I ask you to compare depends on what's going on, but O2 minus will be longer and weaker, and O2 plus will be shorter and stronger. Let's do another one. CO plus. We can do this as long as we're doing 2 atoms and keeping it in the second period, we should be able to do it. Okay. 2 atoms is no different than 2 different elements is no different than the same element. And all that's different is you're counting how you count the electrons. Okay. This has oxygen in it, so we're going to use our oxygen pattern. Right. Sigma, sigma, sigma. I skipped a sigma. 2s, 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 2p. Sorry. P, pi, I, 2p, 2p. That's a star, that's a star, and that's a star. All right. So when we're adding our electrons up, carbon's 4, oxygen is 6. A positive charge means we lost 1. So this is 9 electrons. Put them in there. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Let's figure out our bond order. 1/2 of bonding minus anti-bonding. 1, 2, 3, 4, 5, 6, 7. Minus 2. That's 5. So this is 2.5. Okay. Net bonds. Okay. These two guys cancel each other out. There's nothing in these anti-bondings. So that's 1 sigma and 1.5 i's. So those are our nets. And 1 plus 1.5 equals 2.5. So that makes sense. Paramagnetic or diamagnetic. Well, this guy right here is telling us that we are paramagnetic. Okay. We're going to compare stuff. We did CO plus, so this is 2.5. If we do 2 plus, we're going to lose another electron, so that will be this guy. Okay. And we lost a bonding, so that means our bond order goes down. If we lose a bonding and bond order goes down, this is 2. Okay. If we put this back, now we're at CO plus, and we need CO regular. There we go. So now we have a bond order of 3. You can also calculate this the long way if you want to, but it's going to save you time to be able to do it, adding whatever's. Okay. And again, same thing matters. So CO with no charge is going to be the shortest and strongest. CO2 plus is going to be the longest and the weakest. We need to be able to do this for anything that's 2 atoms in the period 3 or higher. And I say not period 3 or higher, period 2 or period 1. The reason I say that is because once you get beyond the second period, we have d orbitals involved and things just get messy, right? Once you get more than 2 orbitals, two atoms, things get messy. You get more orbitals, this gets a messier picture. And so for bigger things, you'll need to be able to, you can do it by computer. You'd have to do it by computer. Okay. If we're going to do it by hand, then we're going to leave it to these simpler things like what we've been doing. Okay. So what do we need to be able to do? Well, can we recognize and identify molecular orbitals, describe them? How do they form, right? Overlapping orbitals, either end on or parallel, right? So the sigma bonds and pi bonds all still apply here, okay? Draw a molecular orbital diagram, property label, maybe energy axis, and answer our follow-up questions. And that's literally what we did on these 3 examples, okay? You may not want to doodle so much on yours or fix it so it looks nice. So when I grade it, it doesn't look bananas, but there we go. Okay. If you have any questions, let me know. I got one more molecular orbital video coming up, and then yeah. So let me know if you need anything. I'll be here.